So I will acknowledge also the sponsors first. Many thanks to Toyota, Mitsubishi, Seagate, MathWorks, and Qualcomm for sponsoring the seminar series. So today we have the pleasure to have here Professor Yuan C from UCSD. She is at the Electrical and Computer Engineering department at UCSD. I had the pleasure to meet her actually last ACC on the day that you got the NSF Career Award. So it was actually a wonderful moment for me to share this moment. I'm an assistant professor as well, and I know the stresses of of waiting for NSF career. So yeah, congrats again. It was amazing to meet you that day, and lovely to have you today here. So Yuan works on control, dynamics and systems, and applications on power systems, as we will talk today about safe learning and control of power systems. Apart from an NSF career, she has also a Smith Young Early Career Faculty Fellowship, as well as several Best Paper Awards like Best Paper Finalist in L4DC and ACM E-Energy. Excuse me, I'm from a different community, so I need to think a bit. So yeah, the podium is yours, and I would suggest let's keep all the questions for the end of the talk, so that way we can give space to all the wonderful things that we're going to hear. Thank you so much.
Thank you so much. Thank you so much, Vasilis, for hosting me, and it's truly a pleasure to be here. And my name is Yuan Shi. I'm going to share about our work on learning and control for energy systems. I'm willing to hear any suggestions, feedback, questions, and to have a great discussion. To start with, I want to first introduce a bit about the overall research in my group. So my lab first mostly focus on developing machine learning and control algorithms with applications to power grid, building systems, and general intelligence systems. So currently we have two major directions. One is in incorporating stability as a guarantee into reinforcement learning. And this has been found applications in power grid voltage and frequency control. So specifically, we have been using neural networks to parameterize those controllers and learn it in a reinforcement learning loop. And at the same time, we were using control theory to characterize the class of controllers that can preserve the guarantees we like, specifically stability. And we have also been working on those to adapting those policies that we trained in a simulator later on to the real world system, which you may have model mismatch, where the models itself may change over time, like the power grid topology. So those we have mostly applied to power grid frequency and voltage control thus far. Another main direction we have been pursuing for the past few years is on this neural operator learning for control. So neural operator is essentially a new learning framework. So if you think about standard neural network, it learns a vector-to-vector function mapping. And in neural operators, it kind of lifts the dimension and you're learning some function-to-functional operator mappings. And there are various designs, but can all unified under this umbrella. You first project to some finite dimension space, you learn the mapping there, and then you lift it back to the infinite dimensional function space, and they can preserve the universal approximation guarantee for learning those operator mappings, as long as you can show those operators are continuous. And we have been pursuing this direction and have been developing operator learning for control PD systems, for control of nonlinear delay systems, where you're approximating various of PDE and ODE solutions. And also operator learning for fast motion planning, where you're approximating solution of a simplified AJB equation. So I want to talk about those line of work today, and I will mainly focus on the first line of work. So for the operator learning side, we have been also applied for both general PDE and ODE system and building systems. Specifically, this is one building room, and UCSD is a large lecture hall, and you can see the indoor, the right-hand side show the indoor CO2 dynamics, which change with time. And the central area is where the students are crowded, and the CO2 level actually double the safety threshold. And we have been incorporating this kind of airflow dynamics CFD simulations into the control loop in learning it, the mapping, and incorporate into MPC loop for building control. So if you're interested in any of this, I'm happy to connect and chat more. But for today's talk, I will mainly focus on the first part. How do we incorporate stability as a guarantee into RL and use it for power system controls? So to set up the stage, let me ground the talk by this basic reinforcement learning formulation where we use for continuous control tasks. So the goal here is to learn a policy pi theta that maps your state to actions. And then to minimize, in order to minimize this long-term accumulated cost. And then this dynamics here is often unknown. So for example, here, this is in many power system control problems like controlling an EV charging station, data center scheduling, power grid control, we're building HVAC systems. So you have an operator, you don't know the exact system dynamics, you observe the current state, you take an action, you observe how the states evolve and receive some cost function, and you learn this online adaptively. So, and we have a few years ago, we have this collaboration with Caltech group develop a gym environment called Sustain Gym that we develop some RL environment for these different tasks. So one problem with the standard RL formulation when we apply it to control problem in power grid is a lack of stability guarantee. What do I mean here? Because the goal here is only to minimize this accumulated cost discounted, even if your state could become unbounded. Maybe because you train on the finite number of episodes and finite length, it does not penalize enough. So you can still have you can still have instability behavior. So when I say stability is when your system is subject to a disturbance, you want it either converge to some nominal operating point, like 60 Hertz of frequency in power system, or you have a set, like see in the building control, you want to converge to some comfortable range of temperature is a set, or you have some trajectory you want to track, right? Despite disturbance, you want to still track this. So explicitly, we want to incorporate stability as a constraint into the reinforcement learning formulation so that we can guarantee this policy we learned is stabilizing in these scenarios. And in today's talk, I will present two directions to address this problem. The first one is more like we explore the structure. For type of power system control problems, we characterize a class of controllers that is stabilizing. So we will only search within this class. And for the second half of my talk, I will kind of share some of our very recent progress on more general systems. You have a general system F, and how do you learn a Lyapunov function for this F? And we're still trying to see how do we incorporate this Lyapunov as a constraint in the RL loop. So let's start from the first part, the structure exploring part. Let me give a quick motivating example for power grid voltage control. But the idea could apply to other network physical systems later on. So think of a power distribution grid where each node here is a load. It could be a house or building or a commercial facility. And in a perfect balanced world, if the power generation meet the demand, so the voltage at each node stays near its nominal value. For example, for secondary distribution grid is around 110 volts. But in practice, the power grid are consistently faced disturbances. So you kind of rooftop solars and the noontime, other people are generating powers. So suddenly you see, because you're injecting power, so the voltage tends to rise. And after work, when people start to plug in their EVs for charging, drawing power from the grid, you can see the voltage tends to drop. And even worse, these days, there are large computing load connect to the system. And if you see this curve, like even your neighborhood, maybe there is a small company, they purchase hundreds of GPUs, maybe training some models, and their power is fluctuating, also going to cause this voltage fluctuations. So the goal of voltage control is to maintain the voltage despite all this real power fluctuations. You want to maintain the voltage around this nominal value, which is 110 volts. And the mean control actions we consider here is through reactive power. And this is actually, this situation is not hypothetical. Many neighborhoods in Southern California, because we have a lot of large penetration of solars, so they're actually observe this severe voltage oscillations, and utilities are now trying to identify where to install batteries and other resources to manage this properly. So here is a control system architecture for the problem I described. It's a very classical cyber physical system. You have a physical system with a power network, and you have the cyber layer. And then the physical world is governed by the disk flow equation, so which describes how the energy is conserved and each of the nodes, the real power and reactive power, and also how the voltage change from node to node by the Kirchhoff's law. And for the control loop, if there is no communication at all, so each of the nodes just sense the local voltage and decide the local reactive power set point. And then through this inverters, inject it back to the grid. And we're going to see how that change the voltage magnitude effectively. And mean control action here we consider is a reactive power by this inverter interfaced DERs like batteries, solar panels, or like EV chargers if they have bidirectional capabilities. So this problem is actually a very classic problem in power system, and it's studied for decades. And in order to handle this properly, there is this formulated as an optimization problem. For example, we want to find the optimal reactive power set point to minimize the control effort and state violation subject to the disk flow equation, which is a physics. Where some people, to make this problem more trackable, we can use a linear approximation of the power flow equation. It's called the link disk flow model. And then you have the voltage constraint here to guarantee it. So the benefit of this optimization is you can solve it to the optimal, right? If you know everything, if you know the model, if you know the disturbance. And there works, that both tackle this under the centralized case when you have communication, or the decentralized case, distributed case when you only have partial communication. So however, the challenge is for secondary distribution grid, this network topology is often unknown and you don't know the exact disturbance. So solving this centralized optimization is challenging. So on the other end, you can view this as a control problem. Actually, this is where in the IEEE standards, this IEEE 1547 standard basically saying you can adjust your reactive power adjustment as a linear droop control with respect to your voltage magnitude. If you have high voltage issue, let's reduce it. Or if you have low voltage issue, let's increase it. And about 10 years ago, there is the work from Nally and like showing this controller only with proportional term is not enough, because you can always find violations that is not able to be tackled by the proportional term alone. So there are many follow-ups work showing that actually you need to use this controller with both integral and proportional. It's a PI controller. So when you adjust the reactive power set point, it's based on the previous set point and a linear function with respect to your violation. So it's a PI control term. And with this, you can always guarantee, regardless of the disturbance, you can converge to the desired range. And this actually brings in dynamics because we previously only have the power flow equation, but the controller has a memory. So that becomes a closed loop system. But however, because of control, the P term and I term here are both linear and the dynamics is nonlinear. So the cost could be suboptimal. So that is what motivates more recent work on view this as a learning problem. If we formulate this as a reinforcement learning problem, so when we're adjusting our reactive power set points, we're not necessarily need to use a linear PI controller, right? We could parameterize our controller as some neural network that maps the voltage violation to the control action and to do the adjustment. And your goal is to minimize this accumulated control cost. And so in the RL framework, so at each time step, you measure the voltage. And then if there is no communication at all, each node just receives its nodal voltage measurement. It has a nodal neural network to decide the adjustment. And then you will add that to the reactive power set point, and you inject to either the real world system or some simulator of the real world system. And you observe how the voltage being corrected and the corresponding cost. And you do it for trajectory wise, and you use this cost to guide the optimization of your control parameters. So I got interested in this problem a few years ago. So I started to trying out by myself. I take a Southern California test case where they have 5 solar panels. So each one I'm parameterized as a neural network and try to train it using a reinforcement learning algorithm called deep deterministic policy gradients. And within a few hours of training, actually it's converged. So then I start to compare performance with the optimized linear controller. So the solid line here is a neural network. The dashed line here is a linear controller. Actually, without too much effort, I find it's actually improves the optimized linear controller a lot. like it can shorten the, you can see it's faster. Once they have a voltage disturbance, it's dropped back to the nominal range, which is a dashed line here, faster around 30% of the time, and can reduce its transient cost for both of the kits I show here. So it looks very promising. I spent a few days just looking deeper into the behavior and coming up with different test cases. And after a few trials, I actually find there are cases like that are substantially kind of different from the initial conditions or the loading conditions in the training set, but that this reinforcement learning with neural network controllers could feel like this is very common, like because the action is too ambitious and there is no coordination between the controllers. So you can see these oscillations. And also there are cases because without coordination and the neural network behavior out of the training data range, you can see some of the controllers leads to instability. And that is kind of, yeah, please. Yes.
Go back to the previous slide for 1 second.
Yes.
I'm sorry for interrupting.
Yeah,
So then this NN, the neural network which
Yes.
you got from DDPG, that's basically just a state feedback nonlinear controller at the end, right? So it's a deterministic controller.
Yes. Everything here, we are only considering deterministic policies.
That manages this faster convergence.
Right, exactly. It's the deep deterministic policy gradient. Yeah, the policy is deterministic. Thank you. Yeah.
One other question, like in the previous slide, you said linear static feedback doesn't work that well.
Oh,
and
no.
PI is needed.
Right. So this is still maintain the PI structure. So I'm only learning the the P term. So it still maintain this integral structure. So Q is your reactive power injection. So I'm only using the neural network to deciding the adjustments. Yeah, if that makes sense. Yeah, thanks. That's a very important point because otherwise, if you only look at the power flow equation, it's just a steady state equation. So it's only the dynamics introduced by the controller has a memory. So you have a closed loop system, and later on we study stability. Yes.
Comparison you have is with PI.
Yes, exactly. It's only for this UI. Yeah, how the UI. So we're mapping VI to UI using neural network, and then the previous one is mapping VI to UI using a linear term. Yes. Yeah, thank you. Right. That's very important, actually. Right. And I'm talking about the issue of we observe that the lack of stability created actually by the controllers themselves is a deal breaker for real world deployment. So that is where motivate our work, try to incorporate stability as a guarantee into this reinforcement learning loop. And later on, we are also trying to generalize beyond the voltage control systems. But let's first look at this problem. And for the past few years, a structure we identify here is a monotone functions. And I'm going to share with you what are monotone functions and why they're helpful in guarantee stability and how do we parameterize them. So monotone functions in very straightforward for scalar case, if you have a single input, single output function, monotonicity simply means if your input x1 less than x2, so I want my output to preserve the same order, fx1 less than fx2. And for the vectorized case, we define monotonicity in the inner product manner. So if you have a vectorized input x1 and it maps to fx1, and then you have another input x2, it maps to fx2, and then I take the inner product of the input difference and output difference, and I want this to preserve the same order. So that is how we define monotonicity here. And I want to specifically look at why monotonicity is an important structure. And specifically, it can guarantee stability in the voltage control problem. And second is how do we parameterize it conveniently as a neural network? So this is a one-page story of the stability conditions. So we designed this Lyapunov function in this paper. And so this is a quadratic Lyapunov function where the X inverse is a network reactance matrix. So you may wonder, it requires a network topology information, but later on, you're going to see the Lyapunov difference does not depend on it. So, but basically, this is a Lyapunov function we constructed. And then we can, under the linearized approximation model, we can derive this Lyapunov difference. And this has a quadratic form as well. And if this matrix is negative definite, then you can guarantee the closed loop system is stable. And this matrix will become negative definite if your controller satisfies this condition. this is saying the Jacobian of your controller. Remember, this is adjustment term. Yeah, if your controller, the Jacobian with respect to the input is negative definite and also lower bounded by this term. But luckily, this lower bound depends on the control time, sampling time. So if you use a fast enough controller, let's say in the real world, inverters may be controlled at kHz. So this bound become very loose. So we only focus on this part, which requires this controller to be a monotone function, this U. And actually, this you can see this is a model-free structural constraint. So it does not relate to how the network is connected, nor the line parameters. So as long as you parameterize your controller as a monotone function, so you can it becomes a sufficient condition to decay your energy and to make sure your closed loop system is stable. So we kind of talk about why monotonicity can guarantee stability. And the next question is, how do we parameterize this monotone function conveniently? One very straightforward idea is you can design linear functions as long as if for a single input, single output one, if you put the coefficient to be negative, you can guarantee monotonicity, monotone decreasing we're requiring here. But how about a multi-input, multi-output function and also beyond linear? So we parameterize the monotone functions using a neural network where we call it monotone neural network. And how we design it is using this observation. Many of you may take convex optimization before, and you may realize a fact that is a gradient of a convex function is monotone. If this is a convex function, and if you take 2 points, x and y, and you kind of can observe that if you try to approximate function value of y using the gradient and x, it's going to be a lower bound. And if you approximate the function value and x using the gradient and y, it's going to, fx is always greater than that. So if you sum up these two equations, so this is where you have the gradient of this convex function f is exactly this monotonicity condition we are looking for. So we find the gradient of a strictly convex function is actually strictly monotone increasing functions. So that is how we leverage this observation to design what we call the monotone neural networks. So in the machine learning literature, there are all already designs of this convex neural network. So if we look at this, so you have an input X. If it's a multi-layer perceptron model, you do matrix multiplication pass through activation function sigma, and then you go to the next layer, matrix multiplication again, pass through activation function. So if you want this output, neural network output y to be a convex function of x, so what you need is this internal function to be convex and external function to be convex and non-decreasing. And you can enforce that by consider activation function where we use soft plus function here because it's strictly increasing and also convex. And also we restrict all these weights from the second layer to be non-negative, to be positive, to keep the convexity. So if you look at this may be a little bit restricting because you're putting too much constraints. And what we did additionally is we add some residual connection that directly pass the input to all the hidden layers. And luckily, because this is only a linear transformation, so all these weights has no sign constraint. So that is how we represent those convex functions using this strictly convex neural networks. So in our work, we have shown, this is a few years ago in Europe, so we show this construction can give you universal approximation. So it can approximate all convex, strictly convex functions up to very good, any desired accuracy. And what we can do is recall that we can take the gradient of this convex neural network as your control input. And this gives you monotonicity, this structure constraint we ask for stability. And how it works in a voltage control case is you take your voltage measurement and you pass through this monotone neural network. Specifically, first pass through this convex neural network to get Y, some intermediate output, and then you take the gradient. So this is your reactive power adjustment, and you add this to the previous set points. And this, with a minus sign, this is a strictly monotone function decreasing, and it's satisfying the Lyapunov difference condition to ensure stability by design. So by using a monotone network, you can still solve this unconstrained RL problem of whatever your favorite algorithm, but the stability is pre-baked in to the structure of the policy class. So this monotone network is actually very convenient because it can handle different communication architectures. So if you have a network that with full communication, each node can talk with each other. So all you need to do is you take all the voltage measurements of all the nodes. Some system operator fits a centralized monotone neural network to decide the react power adjustment. However, if you don't have any communication at all, each node only have local information, we can still do it. So each node have a local monotone network. So take its local voltage measurement to decide the local react power adjustment. Or if you have partial communication, so this is a communication architecture. So the physical word is fixed. So it's whatever physical connections they are, but this is a communication architectures. So maybe these 3 nodes can talk with each other. So these 3 nodes share all the voltage measurement, fit one monotone neural network to decide the adjustment. So these 2 nodes, if they can talk with each other, so they can fit additional monotone network. The next thing about convex is the addition of the convex function still preserve convexity, so the monotonicity still holds. So we call this a communication embedded monotone network. And we kind of, in our recent work, we show as you have more communication, you're going to observe the performance will improve. So, but you can all unified under this monotone neural network design. So depends on your communication network architectures. So we have tested this using this UCSD DR Connect testbed. Where hardware in the loop simulation. So we take a 13-bus IEEE test case. It's being simulated by the RTDS simulator. And we train those neural networks, this individual monotone neural networks in our laptop. And then load it in the Raspberry Pi, and the Raspberry Pi controls some DR nodes. And here we simulate 2 voltage disturbance. One is a low voltage issue, one is a high voltage issue. And this green band is a nominal operation range we want to converge to. It's convergence to a set. You can see within a reasonable amount of time, usually within 1 second, this controller is able to drive back the voltage to the safe operation range. And how does this compare with the linear controllers and also like unconstrained neural networks? So here is kind of a comparison through this setup. So this blue curve is a linear controller. So it also have, you have this saturation here because once you enter this 5% range, you don't need to, you can just reset there forever. And then this orange curve is unconstrained neural network. You see sometimes it has abnormal behavior. That's why it has some instability issues. And the green curve is where we call stable DDPG, or the monotone network controller. So it maintain this monotonicity, but you can have the different slopes everywhere. So that is can better help with the transient performance. So you can recover the voltage faster compared to a linear optimized controller. So we start from this problem, using this monotone network for voltage control. And we also have some follow-up works that can guarantee not only stability, but you can stabilize to an optimal equilibrium. Because recall that for this set of safe sets, we can, any points can be equilibrium points. And among those equilibrium points, there is one that optimizes the steady state cost, which is a solution of the economic dispatch. We have some follow-up work guarantee optimality there. And also we have some works that can generalize our observation from the voltage control systems to also network systems with the so-called equilibrium independent passivity property. And if your system satisfies this property, there are some examples like power system frequency control or vehicle plutony, or some other examples. There is a textbook actually on this passivity where they give different system examples. But as long as their system have this EIP property, you can also take this monotone controller design, use it as a structural condition to guarantee stability by design before you do the training to optimize performance. So this is kind of the first part of my talk where we show how can we combine control theory and learning, where we have linear controllers. It has stability guarantees, but it's kind of limiting in the function class, so the performance can be suboptimal. And you have neural network controllers, which has a lot of flexibility, but do not have hard guarantees. And where we view this monotone network is here in between. So we have less flexibility than a neural network. So if in a class that you can always stabilize, then it has a slightly worse performance than your standard neural network. But the next thing is it can preserve the same type of guarantees as a linear controller of stability. So, but you are searching within a large class of functions, so you can further optimize the performance. So this is kind of the first part of my talk. We show how can we exploit the structure of power networks, so to guarantee stability of RL. And in the second part, I want to share some of our current exploration on how about this F right now is a more general system. It's not like the voltage control the power flow equations or systems with passivity. So how do you like incorporate stability into the RL loop? And we're making some progress on it. And so far, we have been able to try to learn Lyapunov functions for this general F. And later on, we seek to incorporate it into as a constraint in the RL loop. So let's review. Here, we try to incorporate stability using the tool of Lyapunov. If you have a dynamical system, x dot equals fx, and assume x equal to 0 is an equilibrium point. And Lyapunov stability theory simply says that if this function is positive definite, and if you further compute the lead derivative, the time derivative of this v is negative definite, then you can argue the system is stable. So from the energy perspective, if the energy is always decaying, then you finally reside in this point of the equilibrium where the energy equal to 0. So the question is, how do we find the Lyapunov function? There are many, many methods. So there are existing approach for finding Lyapunov functions analytically. For example, in my previous problems, I find it manually, take a lot of trial and error. So you can, if you have a nonlinear system, you can linearize around all these local equilibriums and use quadratic Lyapunov functions locally. You can use your physical intuition, or for nonlinear systems, if it's strict feedback, you can use backstepping or other recursive designs. Or there are numerical approach like sum of square optimization for polynomial systems, or for non-polynomial systems, you can do some transformation of variables. And there are also genetic programming, other approach. So, so one observation here is there is no single shoes that fits all the fits, because each method works in certain settings and may not work in others. So that's why finding a Lyapunov function for general dynamical systems or some optimization algorithms is still challenging as an open problem in general. But beyond analytical constructions, a more recent line of work is this so-called neural Lyapunov control, where they're trying to learn Lyapunov functions as a neural network. So you can parameterize your Lyapunov function as a neural network. And then because Lyapunov function has two conditions, one is positive definite, the other one is a lead derivative is negative definite. So you can define this empirical Lyapunov risk on samples, right? If you have n samples. On top of that, because we only train those networks on samples, we need to be able to generalize to this compact state space, right? So you will need some formal verification toward there. So this approach is very general. However, so far it suffers from scalability, because now you need to verify a neural network, which may have nonlinear activation functions, a lot of neurons, and also you're trying to argue its property over a continuous state space. So far it's only working for systems like below 6 dimensions. So the interesting point is, if you look at the benefits of analytical Lyapunov functions and the challenges of neural Lyapunov functions, they're kind of complementing each other. So analytical functions, they're super interpretable. It's just mathematical equations. It's easy to verify. You can hand derive the lead derivative or Lyapunov difference. However, it's kind of, have many, many different methods you have to try, and you're not guaranteed to find one. On the other side, the neural approach are very general, right? And you can, even if you don't know control, you can just put a neural network there and train it. However, it's kind of hard to verify, because you verify a large network with many parameters. And at the end of the day, you have a black box neural network. It's kind of do not have much insight about the system behavior. So the research question we have here is, can we kind of combine, can we use a neural approach, but to discover analytical or symbolic Lyapunov functions that kind of have the best of both sides of the world for nonlinear systems in general. Here is a framework we proposed. It has 3 components. So we have a symbolic transformer model. So this will takes in the system dynamics as a language model type of input. And then we'll try to generate candidate Lyapunov functions also as symbolic tokens. And we will generate many of these Lyapunov functions. And then from this, because it's all analytical expressions, we're going to verify those functions and its lead derivatives. And if you're lucky, you find a valid one, then you're good. Otherwise, we will, based on kind of the violations of this candidate have, try to improve this transformer model so that it can give you better and better candidates. And hopefully at the end of the day, you find a valid one. So let's dive into each of the components here. So this is how we encode the dynamics. Take our favorite control system example, like a pendulum. So you have 2 states. X1 is an angle and X2 is an angular velocity. So you have these 2 ODEs. So this ODEs we represent as a symbolic tree. This first dynamics is very simple. It's just X2. The second equation you can represent as a symbolic tree, right? And the node is operators. It's like plus, multiplication, sine, cosine, right? And then underneath is variables, right? Variables or the constant you have. So once you have this expression trees, we do a pre-order tree traversal. So we can convert this dynamics, which is an ODE, to a sequence of tokens. And this tokens is mathematical symbols. And this is how we represent the dynamics. And if you have an nth order dynamical system, you concatenate this sequence, n sequence of expressions into one giant input into your transformer model. And how do we generate candidate Lyapunov functions? We generate these candidates in an autoregressive way. So that is given this dynamics input, given the dynamics encoding, and then given the previous generated expressions, then recursively generate the next symbols in the Lyapunov function. So as an example here, at the start point, both the parents and sibling node are empty. And if the first generated token is plus, then it fits as a parent of the next one. And because plus is a binary operator, so it needs to have 2 children nodes. And then if next you generate a square is a unitary operator, so you know it needs to have 1 more child being generated. So if next you generate a sine, and then next you generate x1, so now you know like this set of the tree is completed. However, this set still needs to be generated. So this is an autoregressive way conditioned on the dynamics and also the previous generated tokens. How do we generate many possible function candidates as a Lyapunov function? So there is a maximum length of generation. So as long as you generate a valid expression or meets the maximum length, so this loop is stopped. So the next thing is now this generated candidates are analytical functions or symbolic forms. So you can actually compute the lead derivative or Lyapunov difference also symbolically. And given both the V and V dot, they are symbolic expressions. They are very effective ways to verify the conditions. So what you can do is you can try to find the minimizer of this function V, and you can try to find the maximizer of the lead derivative. And in order for it to be valid Lyapunov function, you need this minimizer to be non-negative and the maximizer to be non-positive. So if it validates the condition, so you can sample a lot around these minimizers because it's very likely there are also violations in this local neighborhood. On top of that, we also sample a small portion, around 30% across the state space so that it has a broader coverage. And you can verify on this function form, V and V dot, whether the Lyapunov condition holds. Here I want to show you one small example. So this is a process, maybe in some iteration. Our model gives you propose a candidate like this, x1 plus x2 squared plus x2, right? In this local neighborhood, you can see this is a minimizer. 1 and -1. So of course, this is not valid because the function evaluation equals -1, and you can sample a lot around this local neighborhood, this red circle, so to get more training samples. And you can also compute the Lie derivative symbolically. This is the expression, and you find the maximizer, and there's also a lot of violations. And that is how you generate all these counterexamples further on as a reward for how we train those transformer models. And if and some iteration you don't find any violations at all, we can formally verify those expressions, whether they're valid Lyapunov functions. So once we gathered all these counterexamples, we will pass it to this empirical Lyapunov risk, as I mentioned before, right? You can compute on all the samples around this local neighborhood and broader coverage. What is the violation of the Lyapunov positive definiteness condition and the Lie derivative condition? And this is a standard loss function. So we will further bound it to 0 and 1 through this transformation so that it can be used conveniently as a reward function for RL training. So you may be curious, why not we just directly optimize the transformer? Why do we use reinforcement learning? That is because from the token generation to later on, you derive the analytical expression and compute the Lie derivative. Some of the computation steps here are doing by same pi and is not differentiable. So that's why we need to use a policy gradient approach to kind of propagate the reward and to see what is the sensitivity of this performance with respect to the transformer parameters. So we need to use a policy gradient approach. So this is a standard policy gradient objective. So you sample many candidates Lyapunov function, you evaluate the average reward, and you try to optimize the reward. So in our setting, it's kind of slightly different because at the end of the day, as long as you can generate one Lyapunov function, that is good enough. So we don't care specifically on this average performance, but we really want to promote the performance of the top performer. So that's why we use a risk-seeking policy gradient. So for each time, maybe you generate 100 candidates Lyapunov functions, but we only look at the top alpha percent, like top 10%, and how well they perform, and try to do policy gradient to optimize the top alpha percent. That is where we call the risk-seeking policy gradient. So I have just talked about the entire pipeline of our framework. So we embed the system dynamics as symbolic trees and then go through the pre-ordered traversal as a sequence of tokens, put it as input to the transformer model. And the transformer model generates many Lyapunov candidates in this autoregressive way. And because those are symbolic expressions, we're going to compute the Lie derivative and use some optimization tool. Here we use SOGO, but you can also use other numerical optimization tool to find minimizers and maximizers. If you find violations, you're going to use that to construct your rewards to further train your transformer model. And if you ever find a candidate without any violations, we pass through a formal verification process because those Lyapunov functions could be non-convex functions, and some of these optimizers may not always find use a global maximizer. So that's why we will still formally verify it using some tools later on. So this is kind of a summary of our framework. And let me introduce some experiments we did. So the baseline we consider here include both neural Lyapunov tools and also some analytical Lyapunov construction tools. So it includes this neural Lyapunov approach where you parameterize your Lyapunov function as neural networks, and then you verify the neural network, and also some analytical Lyapunov tools developed by also like the SOS tool is a lot developed by faculty in the audience here. And also we test on different systems like the polynomial systems up to 10D, and also non-polynomial systems like van der Pol, quadrators, and also a power system example where very simple, you only have 2 nodes, is a lossy swing equation, but there is no known Lyapunov function in the literature before. And for some of the systems, it's only local stable. So on top of that, you will have a local region when you search for the Lyapunov functions. And this is kind of the mean result we have here. So here, the first column is a runtime. As your system dimension goes higher, your training time grows because the expression you find is also becomes more complicated, and also the state space becomes larger. And the verification time usually is very small because you're just verifying some simple expressions. So verifying them are simple. are not challenging. So here are some fun Lyapunov functions. So on the pendulum system and on the this lossless swing equation, so this Lyapunov function identified are corresponding to the known energy functions. And also we have some fun Lyapunov function that can be verified by looking at them, because you can compute the Lie derivative, and in this region it's obvious to be negative definite. For one of the example here, this is what I mentioned is a lossy power system term, and we don't have a known local Lyapunov function before, and this is one that holds in a local area. And but we're still trying to generalize this to systems with more nodes. Network systems coming with Lyapunov functions are hard because the system dimension grows very quickly. And we also test of this different alpha ratio. Recall this is a risk-seeking policy gradient. So if you set alpha to 1, this is kind of the average, the standard policy gradient. And if you set alpha to 10%, you only care about the top 10% performance. So you can see here, like the risk-seeking really help with the training faster, because you care about the elite samples and it converge faster to find the valid Lyapunov functions. Right. So as a summary, so far we have designed a framework that can generate analytical Lyapunov functions, and by training it through a reinforcement learning pipeline, and by proposing the candidates, and then we use some numerical optimizer to find the local minimizers to verify the conditions. And if you can find counterexamples, you use those to further guide your training. Otherwise, you formally verify it. And currently, our result could scale up to 10D systems and discover some new Lyapunov functions. And there are many ongoing directions we have been pursuing. So one direction we have been extended this to discrete time systems, and actually tried on a few optimization algorithms like gradient descent or heavy ball algorithms, where you can also use the Lyapunov function as a certificate function to verify whether your algorithm converge. So we have tried some of them, and we just submitted to Alpha DC a few days ago. And we have trying to, one direction I really want to try is to combine this learning certificate framework together with the reinforcement learning framework, because one challenge there is a lot of times you need to have an initial stabilizing policy, and then you also ensure in the learning process you always stay in this class. So hopefully with this Lyapunov candidates, we can find an initial stabilizing policy, and then we can solve a constrained RL problem, so you can always stay in their class to find a stabilizing controller. And also I'm willing to see how this could be generalized to other certificate functions, like learning symbolic control barrier functions or other type of certificate functions. And we have a code available. So if you have some system you want to find Lyapunov functions, feel free to try this. And if you cannot find a valid Lyapunov function using our tool, feel free to send me an email. I'm happy to work together, to see whether we can use this tool to help find your, help with your problem, either empirically, where you're trying to find a Lyapunov function for some proof. And that's the end of my talk. So overall, we have been working on this direction of developing learning and control algorithms with performance guarantees for power system applications. And I really appreciate your time, and I'm looking forward to answering any questions you may have.
So this Lyapunov toy is really cool, I should say. I have a couple of questions. So it looks like that you do have some kind of library you are choosing these functions from. Is that
exactly? Is that so like the library is a token. So it's not like I think in our talk today you mentioned Sandy. So Sandy is you design all the bases and you do a sparse regression. Right. But here, like you have a library, but this library is just some basic operators. For example, we put plus sign here, multiplication, and square, like all the state variable. If you have an ND system, you have x1, x2, xn, but you don't need to put x1 square, x2 square, x1 multiply x2, right? All those are formed based on this autoregressive generation process. So your library have some basic operations. So far, we mostly have plus, multiplication, sine, cosine, polynomial terms, and the variables. And we are trying to incorporate also log and division, but they still have some numerical issues because log once you have negative numbers. But yeah, this I also so you do have a library, and the library is a chance you can incorporate your prior knowledge. Yeah,
that makes sense.
Right.
My real question is more about when we construct a Lyapunov function,
Yes.
let's say close to an equilibrium,
Right.
it's always locally some kind of quadratic thing. Right? So, and that's what you also, some of your results are also actually that. But then once we want to talk about something like region of attraction, well, it's true I can put whatever Lyapunov function there, but I can only guarantee this region of attraction if I have some class K functions to bound. So my question is, did you think about like kind of bounding these functions in one way or the other? Because that would look more useful in many applications in my mind, if you can do that.
Yeah, I think that's such a nice question. I think we're also trying to incorporate this in the learning curve, because right now, if you can come with, for one system, you can find many Lyapunov functions, but you want to find one that has a large region of attraction, right? So hopefully that if for one Lyapunov function, if you can kind of characterize the region of attraction, you can incorporate that into the reward function. So you can, in the learning process, you can try to find a Lyapunov function that has a large region of attraction. I think that will be the goal, where that will also be helpful in the controller search. You want to find a controller that has a, but so far, I think we haven't been able to do it because we don't have a good characterization based on the.
Actually, in your first part of your talk, you were talking about this monotonicity, right?
Yes,
so in some sense, the nice Lyapunov functions typically have some monotonicity feature. So maybe you could combine the two and somehow bring in that monotonicity into the Lyapunov design that allow you to have Lyapunov functions which can give you large area of region of attraction.
Right. That's very nice point. The quadratic Lyapunov function actually has a name. It's called Krasovsky's. I think that, but it's also limited to a class of system where they admit Krasovsky's structured Lyapunov function, right? Yeah, but I love to incorporate ROA and enlarge this ROA into this search loop.
Thank you.
Yeah, thank you. Yeah, please.
Yeah, so I'm just learning today about neural network-based Lyapunov function generation, and but thank you. It's very interesting. So my questions will be very basic, given that my knowledge was very basic going in. But so one of the things I saw in your risk function, I think you called it, you've got two terms. I didn't see any weight between those two terms, and the first thing that came to mind is that the Lie derivative has got units of an extra unit per second, basically, because it's a v dot term. And so is it when you're constructing that risk function, is it advantageous to select a weighting that reflects the time constants of the system such that the two terms are balanced? Like if the system is super fast, then the term that has units of rate is going to be very, very large and dominate the other term. I just wonder if you looked at that at all.
Oh, that's a great question. Yeah, I think you can add a weight here, but I wonder, actually a lot of the work also in this original neural Lyapunov control, they were just using this empirical Lyapunov risk, which just combine them in a weight one way. But I think that's a very valid point. And I guess that weight can also be tuned per system basis, right? Yeah. So I think that will be a nice nice way to try out and see how that maybe help with this more effectively.
Cool. And as I understand, so in order for the Lyapunov function to be valid, for showing asymptotic, both of these terms of the risk function have to be zero.
Yeah, exactly. So you're minimizing your error to zero.
Right. What happens if, in practical scenarios, we do stability analysis to see whether the system that we've designed, the closed-loop system that we've designed with the controller, is actually stable. So we don't actually know beforehand if the system's asymptotically stable. So there may be systems that you throw at this where no solution exists, right? Is there sort of an expectation that when you use this tool, you strongly suspect your system to actually be asymptotically stable, and therefore there must exist some Lyapunov function? And what happens when you throw a system that's actually unstable at the tool?
Right. I think if you throw this message to a system that is not stable, like you may not see this error, this loss function converging. In our message, you may not see the reward converging, right? Yeah, that is if the system is unstable. But the other side is not necessarily true. Like if you does not see the loss function converging, maybe you're not using a good enough learning rate, or maybe it's not. Yeah. So the other side is not true. If you cannot make this process converge to a valid Lyapunov function, it does not necessarily say your system is unstable. Yeah. Okay.
Last thing.
Yeah.
I was gonna jump in with this, but I didn't want to bug you with it during the presentation. In your voltage control law, where the law takes on the form Q sub I at time step t plus 1 equals Q sub I time step t plus a correction term. You're referring to that as PI control, but is that just I control?
Oh no, it also has a P term. Let me see. Yeah. Sorry. Yeah, sorry, I didn't make it clear. Yeah, because this function is a linear function and you're responding to the simultaneous voltage deviation. So this is a P term and this is kind of the integral.
No, I don't. I disagree. So if you're doing PI control, you would need to have a separate state variable.
Oh, so I think I should call this is a controller with memory term, right? Yeah, maybe this is more proper. Yeah, the controller. Yeah. So essentially in this paper, they're saying the linear controller but need to have memory. Yeah. And this memory maintains your previous set points, and then you are just adjust to the simultaneous, instantaneous deviation. Yes. That, yeah, thank you. Thanks for. I think it should be say with memory. Yes. Yeah. Oh, so the integral, you're more saying I should integrate to this previous deviation. Yeah. Right. And it's not explicit, but it's implicit because this QI is this QT minus 1 depends on QT minus 2. And that is, so it's implicit. Okay, cool. Yeah, thanks. Yes.
Can you extend your tool so that you can actually prove conversely Lyapunov errors? So for example, if you have a system that you suspect is unstable, can you use this tool to prove that it's guaranteed to be unstable by finding there's the converse Lyapunov functions that tell you that if you find a function that decreases within an open neighborhood of the origin and you know what I'm talking about. Can you extend this to those kinds of problems?
Right, I haven't thought about that, but I think I want someone propose like a converse Lyapunov idea to me. We haven't tried. It's more like maybe the converse Lyapunov function give you a construction for a system. You have a trajectory, and then you can use that maybe to learn this Lyapunov function. But I haven't thought about the connection. How can I use my tool to prove the system is unstable? Right. Thank you.
So as far as I understand, you are using this like global optimizer. I was thinking it SHGO inside the loop, but it's not slowing things down. So it's solving a nasty optimization problem and not slowing things down.
Right.
My question is there a way to like write a big optimization problem that also searches for your Lyapunov functions parameters and just throw it to SHGO? Like using this SHGO to solve smaller problems in the loop.
Oh, I see. And then how do you parameterize your Lyapunov functions?
I mean, you are in a sense parameterizing with these templates, right? I can put a bunch of like in the end you are getting, as far as I understand, polynomials of certain degree. I know how to parameterize polynomials of certain
and
degree.
Also sine, cosine. You can put sine, cosine exponentials. All this are in our library. Right, but I think one way is actually to combine with the earlier question. Maybe you can have in our case, we have a library and this library is only basic operations. But if you think about the other extreme, you can have a set of bases and that can be very big set of bases, like hundreds or thousands of terms. And you put the coefficient there and you can put some of the sparsity regularizers in the end. And then you can try to combine the coefficient and have the lasso regularizer and then put it in this SGO loop and to search for a system. Yeah. I wonder that will be the Sandy way for finding Lyapunov function versus this kind of transformer way of autoregressively generating by combined basic operations. Yeah, I don't know how we'll compare, but I think that's an interesting idea to kind of try, because both are symbolic functions. Yeah. Thank you. Right. I think I think you have the question way early. Sorry.
First part is about how to design a controller and optimal controller, and the second part is how to design a Lyapunov function. So can we do these two tasks simultaneously? Such that so we use a joint optimization objective, which is consists not only the cost term, like the deviation between the maximum or the minimum,
Right.
and the Lyapunov term, like so, and the output of the Lyapunov risk loss.
Right.
We optimize this both in the reinforcement learning.
Right. Yeah, that is what I really hope to do, actually. Yeah, I think I put this slide in the very beginning. So the first part is because for the system, we know we construct a Lyapunov function. So this constraint become like a structure constraint. And then we already can guarantee this by design, so we can optimize. But now for general system F, I don't know how to, I don't even know where constraints this is. So now we're kind of searching the Lyapunov functions. And then later on, we have a constraint optimization, but that is where you mentioned is where we really hope to do. As we're learning this controller, we're also simultaneously learning some stability certificate, and then you can first find an initial stabilizing policy. And then as you're improving, you always stay in the stabilizing class. Yeah, that is where we hope to do. Yeah. Thank you.
We're
Why do we do this? Just